So this is actually very early in the book's reading. We get into section 1.1.1.1, Boolean Algebra. It talks about the Boolean algebra, the values are labeled true, false, 1, 0, yes, no, on, off, and so forth, right? And then it doesn't take long before we see some really scary stuff. Like, what is this right here? So, and they're talking about tuples. What are tuples? It doesn't really explain what tuples are. Tuples are related values in a data set, right? So you can have related values in a data table or a data set, and those are collectively called tuples. Another way to think of a tuple, I think, is a record in a database. So it's talking about the columns gives the value of the thing. And when we talk about data tables, here's what we're talking about in real terms. Okay, so this is a Boolean function table which has two input variables. Okay, now what do I mean by variables? Have any of you had algebra and you have this a plus b equals c squared kind of thing, right?
Yes.
Okay. So when we talk variable, we're generically talking about this could be variable 1 could be input 1. And variable 2 could be input 2. Or variable 1 could be a. Because, you know, there's a strong connection between math and computer science. I know some of you might be getting a little queasy hearing that, but it is true. The logic of Boolean discrete math was discovered about 150 years ago by a mathematical genius. And he basically figured out Boolean logic. And this gentleman revolutionized the world. He didn't know it, but 75 years later, somebody would start talking about logic in a computing context. And if the mathematical researcher had not come up with discrete mathematics, logic mathematics, the mathematics of true and false symbolically, we wouldn't have computers today. But I want you to think of inputs or variables. When we talk about variables, when we're talking about the basics of computer architecture and Boolean functions or operators, right? There's some very clear distinctions. A logic gate is the same as a software Boolean operator. So you have a software equivalent and a hardware equivalent. Either way, they both have inputs. And you could label the hardware input wire A, and it's literally a copper wire A, and copper wire B. And because there are two inputs, what's 2 squared? Anyone?
4.
4. There are 4 possible combinations of inputs. If A is 0 and B is 0, if the electricity is turned off going into wire A, if the electricity is turned off going into wire B, then the answer coming out would be 0, because there's nothing on going in. And that's for a case we're talking about the Boolean operator or, okay? For the Boolean operator or, no, yeah, all right. We'll take or first. The Boolean operator or is software. It's an equation. It's a statement in a programming. You know, you can basically do it in software, right? The logic gate is hardware. It's physical. There are materials in nature that you put together and it creates a Boolean it functions like a Boolean operator called or. So if we're doing a truth table, and this is a truth table, right? We have a column A because we've decided to call the first input A. All right. We could say that we're going to call the first variable or input A. Okay. So this is the Boolean operator or, and or input B. Now, before you start seeing cross-eyed, what I want you to understand is that or is there are 3 unique Boolean operators and 3 unique logic gates that make all of the world go around. Remember the subatomic particles, protons, neutrons, and electrons? You have binary values, 1 and 0, and then you have these operators or functions, right? These logic gates. And if either of the inputs, if input A is a 1, or input B is a 1, then the output, the answer, is a 1. Let's say that again. I want you to see this. It is verbal and logical and mathematical. Think of what the word or means. If input A is a 1, or input B is a 1, then the output is a 1. Now, for this case right here, we have 4 possible, if we have 2 inputs, A and B, 2 squared is 4 possible combinations. So we have a case where input A could be 0, input B could be 0, or we have a case where input A could be 0 and input B could be 1, or we have a case where input A could be 1, turned on, the wire could be lit, current could be flowing, or input B, the wire, the copper wire, in the hardware logic gate is turned off. So A is off, but B is on, or A is on and B is off, or A and B are both on. But let's look at the output. If I look at the output, in this case, both A and B are off. So what's our output? Based on that logic for OR, based on the logic I just explained for OR, if any of the inputs, any of them, are turned on, then the output is turned on. So what represents on? 0 or 1?
1.
1 represents on. But do I have a 1 for input A or a 1 for input B?
No.
No, I don't, right? And that means the output is also off. Let's look at this case. Input A or input B. If it's on, then the output is on. What's the output here?
1.
1. Okay. How about input A is turned on or input B is turned on? Well, in this case, input B is turned off, but input A is on. So what's our output here?
1.
1.
1.
1. Okay. What's our last case? Both input A and B are turned on.
1.
1.
1. Okay. This represents OR. The Boolean operator called OR, which is also on a binary level the same as addition. Let's repeat that. OR is the same as addition. The mathematical operator of addition on a binary level. All right, so, and we're going to talk more about that in a minute, but before we get further, I just want to make sure everybody has this squared away, right? Everybody good? So what does that look like in your book? I'm gonna fast forward, and I want you to skip over this right now, right? So when it talks about V1 through talks about V1 through Vn right here. The V1, it's this right here. This is V1. This is V2. You could have V3, V4. You could have 3 inputs, 4 inputs, 5 inputs. We'll talk about that in just a second. Okay? In fact, let's talk about it right now. Let's say we have an OR operator, right? Whether we have hardware or software, let's say we have input 1 or V1, variable 1, right? And all the values, all the possible values for input here, right, are listed. What's 2 to the third? We have 3 inputs. What's 2 to the third? Please. Cubed. What is it? Yes? What is it?
8. It's an 8.
It's 8. You have 8 possible combinations. You have a case where all 3 inputs could be turned off, all 3 inputs could be turned on, and you have other combinations in between, like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Does that sound familiar? 1, 0, 0. That's like the binary for 0, 1, 2, 3, 4, 5. Aren't those the binary values for those numbers? Yeah?
Yes.
Beautiful, beautiful analogy there. You want another comparison that really helps? Watch this. What do you notice about the first column for the possibilities?
Wait, that's 15.
See, you have the first 4 inputs for input 1 here are all 0. The next 4 inputs for input 1 are all 1s. Look at the second column. 0, 0, 1, 1, 0, 0, 1, 1. See the difference? And then look at this one. 0, 1, 0, 1, 0, 1. Right? See, I want you to be able to fill out what's called a truth table. This is called a truth table. A truth table tells us whether our output is true. A truth table is used to determine the possible combinations that result in a true output or a 1 output. And for the OR Boolean operator, if any of the inputs, if input 1 or input 2 or input 3 is a 1, then the output is a 1. That's OR. That's how OR works. Any questions? Let's fill out the outputs for OR Boolean operator on a software level, or the OR logic gate on a hardware level, with instead of 2 inputs, it has 3 wires going in and only 1 wire coming out. What's my output here for the first case?
0.
Why?
Because you have 3 0 inputs.
Yeah, you don't have any of them. 1 is not, 2 is not, and 3 is not. What about the rest? Look at all the rest.
1. They're all 1s.
They're all 1s.
All 1.
See, that's interesting. Now let's do a little flip here. Here's an OR logic gate. Also the Boolean operator, OR, with 2 inputs. The first one is 0. What are all the rest?
1.
1s. Well, let's take it a step further. Let's do a 4 input OR. Okay? Are you with me?
Yes.
Whether you have hardware or you have an electronic component called a logic gate, if we had 4 variables or 4 inputs or A, B, C, D or E, F, G, H, use any kind of letter, any kind of word, any kind of number you want to represent the variable inputs, the wires that are going in. If I have, watch this, are you ready? I just think this is cool. Here's another pattern for you. When you fill out all the possible combinations, I have 0, 0, 0, 0, or I have 0, 0, 0, 1, where the last variable, the last input, input 4 is 1, or I have 0, 0, 1, 0. Okay, so that's binary 1, that's binary 2, that's binary 3. Look, do you see a pattern? In the first column, half of the are what?
All 0.
All zeros. In the last half of the column, what are they?
1s.
All ones.
All ones. Now look at this next column. 4 are 0, 4 are 1, 4 are 0, 4 are 1. Look at the third column. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Look at the last column. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, all the way down. Right? Okay, let's do it. In the first case, if input 1 or input 2 or input 3 or input 4 is turned on, then the output is on. What do I have?
0.
I have 0. What are all the other values?
Ones.
Ones. That is how OR works. If an input is 1, or the next input is 1, or the last input is 1, however many inputs, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 2 to the 27th inputs, v to the 27th, right? Oh my gosh, that's a huge number. You have so many different values for that. You have, like in this case, we have 16 records. In this case, for 2 inputs, we have 4 records or tuples, right? They're using different language to describe this. With 3 inputs, we have 8 tuples or records of possible outcomes. In the case of 4 inputs, we have 16. How many do you think we'd have if we had 5? Let's see, we had 4, then 8, then 16, then what comes next?
1, 1, 1, 1, 1, 1, 1.
Yeah, you have 5 inputs. It's 2 to the 5th. How many combos do you have then? You don't have 4, you don't have 8, you don't have 16, you have, see, we're doubling each time, right? What's twice 16?
30.
32. Continued on the next page. I have 32. What can I tell you about the first half of variable 1? Oh, it's all zeros, 16 of them in a row. What about the second half of variable 1 or input 1? Oh, they're all ones. How about this? Oh, 8 are zeros, 8 are ones. What about the next set of options, right? The point is that you use these truth tables to break out the possible options. What's my answer for OR here? Not rocket science, come on.
0.
Yep, why?
Because all the inputs are 0.
Yep. Same thing. 0 and then 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Whoops, I missed one. Now, you're probably saying, okay, this is getting boring. Yeah, okay. Let's, by the way, this right here, everybody see this right here?
Yeah.
Can everybody see this function f? What do they choose to decide to use for the input labels here for the Boolean function or the Boolean expression? Are they using 1, 2, and 3?
No, X, Y, and Z.
They're using X, Y, and Z, but we have 3 of them. So which truth table am I going to use? The one that has 2 inputs 3 inputs or 4 inputs or 5 inputs?
3 inputs.
3 inputs.
I have X, Y, and Z. That's 1, 2, and 3 inputs. Therefore, I'm going to use the truth table with 3 inputs. Everybody see that? And X, see, I can simply go like this. Okay, for that scary stuff, input 1 is going to be equal to X, right? Input 2 is going to be equal to what? Y. And input 3 is going to be equal to Z, right? I'm doing the same thing. I'm putting in the possible options, the possible answers, the outcomes, if I'm using an OR. The tricky part here is understanding how your author, they're using different terms. So tuples means possible records or combinations, right? Possible combinations. This thing right here, we're going to take some time building up to how we break that out. So when you get into your textbook, it's talking about X or Y and Z, not. We have 2 other logical gates or 2 other Boolean operators to discuss. We talked about OR right here. We talked about OR. I'm going to share with you what AND does. Are there any questions about OR? Everybody understands it's whatever input, if it's 1, or the second input is 1, or the third input is 1, or the fourth input, doesn't matter. OR means, except for one case, they're all going to be the same. All right? Everybody good?
Yeah.
Okay. Now let's change it to AND. And the second juggernaut, the second component of the Boolean operator, the second basic of 3 different logic gate types, hardware, and, or Boolean operator, and, it's actually the mathematical equivalent of multiplication. And that becomes confusing because people are saying verbally and. It's represented by a dot or an asterisk instead of a plus sign. So OR is represented mathematically with a plus sign in an equation, which I hate. It's like, oh, come on, you math guys, you mathematics professors, can't you do something that's just consistent for a change? If I'm talking about and, I should use a plus sign, right? No, that's not how it works. For 50 years since they started computing, it's a little confusing, but what I want you to understand is that the plus sign in an equation, the plus sign in this equation right here, that means or, not and. Even though we tend to logically think of a plus as an and when we're talking in a sentence, right? Just remember that or is if input 1 or input B or input C or input D or input F is a 1, then the output is a 1. So how does and work? With and, they both have to be 1 for the output to be 1. Input A and input B has to be 1 or true in order for the output to be 1. So let's walk through it again. Here's the truth table for and. In this case, what do I have for an output?
0.
0. Neither A nor B is a 1. So my output is a 0. What about this one?
0 as well.
Input A has to be 1 and input B has to be 1 in order for that to be 1. Is it?
So we have a 0 for the output.
We have a 0 for the output because input A is not 1. How about this case?
Same thing, 0 again.
Oh, see, the input B doesn't have a 1. Both A and B have to be a 1, so the output is 0. What about this case?
We have a 1.
Have a 1. Okay, everybody with me so far? Let's go. We're almost done. Let's do and. And let's do and. What about this? What's my output?
0,
0,
What about the next one?
0,
What
0,
about the
2,
next one?
0,
0,
Because,
0,
0,
because input 1 and input 2 and input 3 all have to be true or 1 or on. So this is a 0, this is a 0, this is a 0, this is a 0. What about this one?
that one is a 1.
Do you notice a pattern? What do you think? You notice, everybody notice a pattern? What's true here if I go and? If I'm talking about and instead of or? I have 4 inputs now. How many possible combinations do I have with 4 inputs? 2 to the 4th? What's 2 to the 4th? 16. I have 16 possible combinations. Here they all are. And here's their breakouts. Input 1 and input 2 and input 3 and input 4 have to be a 1 in order for the output to be a 1. What do I have?
0,
0. What about the next one?
0,
0, 0,
0,
0, 0, all the way down,
0,
all the way down, all the way down.
until the last column. Yeah,
1.
1.
You notice a pattern. Any predictions on the last one? If I go and,
You're gonna have zeros all the way down until the last one.
it's going to be different. Instead of the or, they're all going to be zeros. Except for the last one. Notice a pattern. Even this one, because I have a 0 right here. But now, starting with this one, is it any different? No. All the way down except for the last case, 1. That's it. That's the only one. All right. So this concludes our review of or, our review of and. You can have multiple inputs for or, you can have multiple inputs for and. Not is real simple. Not doesn't have a truth table. Not simply reverses whatever is going in so that it's the reverse of what comes out. So there is no truth table for not, unless you have multiple inputs with not. But let's not go into that right now. What do I mean? Let's say for not, all right, so not doesn't have 2 or more inputs. Not only has 1 input and 1 output. So not is different. If your input is a 0, what's not 0?
1,
If your input is a 1, what's a not 1?
0,
Let's repeat that. It always reverses the input and gives you the other value. So if I put in a 0, what do I get coming out? I put a 0 in, what comes out? There's no table. I don't use a truth table. What's not 0?
0.
What's not 0 in the
1,
binary world?
1.
It's a 1. What's a not 1 in the binary world?
0,
This value is not 1. In the binary world, what's the only possible alternative?
0,
0. So not only has 1 input and only 1 output. And in terms of logic gates, here we go. What does it look like as a physical device in the real world? We're going to fast forward. So it talks about logic gates now, right? Gate logic, that's the physical device. This is the symbol for and, right here. This is the symbol for or, and this is the symbol for not. In this case, the and has two inputs, A and B, and it has one output. If I chain them together, I have three inputs, A, B, and C, and one output. If I chain another one in here, I can have four inputs. So just remember, if it's rounded on the front, like a handgun bullet, or half a circle, that represents the and. If it looks like a pointed bullet, like a rifle bullet, or an assault rifle bullet, heaven forbid, right? That's an or. And the not is triangle shaped with a little mini circle in the front. Whatever goes in, comes out, is reversed. So it's a reverse gear. If it's a one that goes in, and a zero comes out. If a zero goes in, a one comes out. A not one is a zero. A not zero is a one. Those are the physical electronic components that operate just like the Boolean operators. And is represented in Boolean terms with a dot, or is represented in Boolean terms with a plus sign, and not is represented with a line over, a line over, a line over, x not. That means the value of x is knotted, okay? So yeah, let's stop there. See here you see z with a line over it. That's a knot that goes into the z. We're going to explain that more in detail later. The thing I want you to know in plain terms is, what are the outputs for or? What are the outputs for and? If there are two inputs and one output, what are the outputs for or? And what are the outputs for and if there are three inputs? If there are four inputs? If there are five inputs? 6 inputs, 7 inputs. You need to be able to fill out those tables, right? And if you're gonna, I'm gonna give you blank tables and I want you to fill them in. And you're gonna go, oh no, I can't do that. Yeah, you can. Depending on the size of the table, the first half of the first column are all zeros. The second half of the first column are all ones. Then half as many are zeros. And half as many are ones. Any questions about the combinations that are possible when you're using logical operators or and then not is real simple. No tables. You don't use tables for not. There's just one input and one output. Any questions? Think of it as multiplication, division, and addition, and that's all we have to worry about in the logical world. Or, and not, in logical terms. Okay? I'm going to go ahead and stop sharing here. I'm going to stop the recording as well.